Welcome to Empowered Learning. This video will be our introduction into higher order ordinary differential equations. And to be specific, what we are going to talk about is how to use substitution techniques for higher order ordinary differential equations like second order, third order, fourth order. And we're going to leverage what we already know about first order ordinary differential equation techniques. So if you have been following the videos that I've been doing on this particular subject, then you know that at this point you should be familiar with most of the first order differential equation techniques. And so that includes solving separable ODEs, directly integrable ones, ones that are first order linear, all the ones that you do via substitution, like the homogeneous ones, ones where you have linear substitution, as well as your Bernoulli equations. So all those equations that I named are first order ordinary differential equations that if you're watching this video now, you should be familiar with how to solve those types of equations. If you're not, you may want to go back and look at those videos and take some time to learn those techniques and then come back to this one, because we will be leveraging all those things in this particular video. So one of the things that I want to get across here is that with this being an introduction to higher order ODEs, naturally after we study first order ODEs, we want to go to second order ODEs. And so when we get deep into studying second order ODEs, you're going to see that a lot of the techniques that we use in this particular video won't necessarily be used per se to study those other more important second order ODEs. And just to kind of let the cat out the bag a bit, it'll be linear second order ODEs with constant coefficients will be one of the main ones that we study. We will also study what's called Cauchy-Euler, or some people just call them Euler equations or Cauchy equations. But those will be another type of second order ODE that we will study as far as how to solve it, but it won't be in this video. My point being is that for those special types of ODEs, we have specific techniques that we use to solve those. What we're trying to do is sort of handle, all right, well, aside from those more important ones, here are some other ones that pop up, and we're just going to put them all in one big catch-all type of group and say, all right, well, these are all the others. And so we're going to take care of these first, and then after that, you'll see in the videos that come after this one that we'll talk about second order linear ODEs with constant coefficients, and then Cauchy-Eulers, and then of course we'll kind of build upon that from there, and eventually talk about non-homogeneous ODEs with constant coefficients, and so on and so forth. Okay, but I'm saying all that just to kind of set the stage so that you know what it is that we're going to be focused on here. And again, it is essentially second order ODEs where we can use substitution techniques like how we do with a lot of first order ODEs to be able to solve them. Okay. Now, the categories that we're going to put these particular ODEs in, two of those three categories are listed here. So this first one here is going to be ODEs where we only see terms that either have an x in it, a y prime in it, because that's what dy over dx is, or y double prime in it. Okay, and this says and, but it really should be and or. Okay, so as long as each term that we have either has an x in it, and or a y prime in it, and or y double prime in it, there's going to be one technique for that. Okay, and another way to think about that is you look in each term in your ODE and you see no explicit reference to y. Okay, and notice that when I say no explicit reference to y, if you see a term with y prime in it, that's different than y. Okay, if you see a term with y double prime in it, that's different than y. So you literally have to see something with just y in it to be able to say, all right, well, that's not what we're talking about here, okay? So if you see something with just x, or a combination of x and y prime, and or a combination of x, y prime, and y double prime, then it's this first type, okay? Now for the second type, again, either we see a term with y in it and or y prime in it and or y double prime. Or to put it real simply, we see all of our terms do not explicitly show x in them, okay? That will be the second type that we'll study. The third type will just be sort of the same thing, but it'll be a variation of a theme on that, because we will start to look at what it looks like to solve third order and fourth order ODEs that are of the same ilk, okay? All right, so before we get into actually doing these techniques and going over what those techniques entail, let's go over a few definitions here, okay? So when we say we have a second order ODE, all we mean is that we have an ordinary differential equation where the highest derivative in any term is a 2, okay? And of course, for third order, the highest derivative in any term is 3. And we say that that it's of order 3 when we do this. So that's why you see this word order here, okay? And of course, if we're going to the nth order, that's, just random or in general, then of course it'll be of order n, okay? Now some examples of what second order and third order ODEs look like. Of course, you'll see these here, and this should have a double prime on there like that. So for here, this is what second order looks like here. Highest derivative of a highest order is 2. Here, highest order again is 2. Here, even though you see the squared here, that doesn't count as a derivative, okay? The highest order of derivative we see here is 2, okay? And of course, for the third order, highest order derivative is 3. Highest order of derivative is 3. What you see here, so if you don't recognize this here, this is saying we have a sixth order ODE. So that's my example of saying something that's higher than third order. And of course, this is the 41st order. This would be 41st order ODE. Again, don't see why we would need to do anything that high as far as derivatives are concerned, but I wanted to just give you some examples there, okay? All right, so let's move on and let's talk about these techniques. So substitution techniques for second order ODEs. So as we study techniques for solving higher order ODEs, we will see that the techniques we learn for solving second order ODEs will be most important to us. We'll also see that most of the techniques that we learned to deal with first order ODEs won't directly apply to the ODEs that we will deal with in the second order type. So basically what I'm saying is that all those ODEs that I mentioned, like the separable, directly integrable, Bernoulli, homogeneous, so on and so forth, those techniques won't be directly applied to the types of equations that we deal with when we get to second order, third order, fourth order, so on and so forth, okay? And we're specifically talking about the second order here because we're going to study that for a while. However, there are two specific types of second order ODEs that lend themselves to possibly being solved via substitution techniques, okay? And these techniques were introduced whenever we went over first order ODEs. So the point that I'm trying to make here is that when we study first order ODEs, remember when I mentioned, hey, we studied how to solve first order linear ODEs where we need to do linear substitution. When we recognized we had a homogeneous type of first order equation, as well as when we had a Bernoulli, And if you remember watching those videos, I called the Bernoulli a first order linear ODE with an identity crisis. Okay. And so for those types here, we're going to see that if we do the proper substitution for the ODEs that we're going to study here, these second order or third order or fourth order ODEs will turn into one of those earlier types of equations that we learned how to solve. Okay, and that's the main point that I'm trying to get here. Now let's look at the two types of ODEs that we're going to deal with. Okay, again, we're going to be dealing with ones where we see no y in any term, and then we're going to be dealing with some where we see no x in any term. Okay, and so we're going to concentrate on looking at the ones with no y in any term first, and then we'll concentrate on the ones where we see no x in any term. Okay. So the easier of the two techniques that we have here will be the type where we essentially see no y in any term. Okay, I'll just say it like that. So the first thing that we recognize here is that if we see no y in any term, then we either just have x, y prime, or y double prime. So what we want to effectively do here is we want to change the ODE that we're dealing with from a second order ODE down to a first order. Okay, and we want to do that because we know how to solve a lot of first order ODEs at this point. Okay, so we're trying to leverage what we know. So what we do here is we say, all right, we see that the lowest order of derivative that we have is first. So we say let v be the derivative of y with respect to x. And another thing I want to put here is that we're assuming that v is a function of x. Okay, and so I'm mentioning that because that's going to affect how we take derivatives of v. Okay, in the other technique that we're going to study, we're going to assume that v is a function of y, and that's going to change things. So that's why we need to make sure that we understand that. So if we know that v is going to be the first derivative of y with respect to x, and v is assumed to be a function of x, then of course the derivative of the derivative, or the derivative of v in this case, is just going to be the second derivative of y. Okay, so simply put here, if v is y prime, then v prime is y double prime. That's another way to put it. Okay. From here, we make the substitutions that we need to. And so when we do that, we're going to see that this dy over dx, or y prime, is just going to be v. Anything that has the second derivative of y is going to be v prime. Okay. And of course, that's why I have this here. And then, of course, now we see that the highest order or the highest derivative of any term is going to be 1. So we can now use all the first order ODE solving techniques that we know of. Okay. And of course, what we're looking to see is our first order ODE going to be separable, directly integrable, a first order linear one, first order homogeneous, or Bernoulli, or first order with linear substitution. Okay, so those are all the ones that we've studied up to this point. After we know which one it is, we just use the appropriate technique to be able to solve it. Now, one last note that I want to say before we go on and talk about briefly the other technique for the other type situation. In solving for general solutions for second order ODEs, we want to be mindful that if we're solving for general solutions again, we're going to have two constants of integration. Okay, so notice that whenever we had the first order ODEs, when we were solving for general solutions, we only had one constant of integration, but now we have two. And of course, with the initial value problems that we deal with, instead of having just one initial condition, we are going to have two initial conditions now. And of course, that makes sense because if we have two constants of integration, and we have an initial value problem, we need to figure out what those actual constants are. So we're going to need two pieces of information to be able to do that, since we have two unknowns. So for our second type of second order ODE that we're going to deal with here, in this case, this is the one where we see that we have no x in any term. Okay. Of course, another way of saying that is that we only have terms with either y prime, and or y double prime in them. Now, one of the things that we can do here to make sure that we remember one of the most important things in this particular technique, and that is to assume that our substitution v is going to be a function of y at this point. Notice that we have y prime, and y double prime. Since we don't see any x here, it is safe for us to call this an autonomous type of ODE. Okay, and of course, autonomous just means that you don't see the independent variable at all, okay, in the equation. And of course, in this case, we're assuming that the independent variable is x. So, thinking of that, our first thing that we want to do for equations of this ilk is we want to say that v is going to be a function of y, but let v be the derivative of y with respect to x. Okay. Now, if we think about that, what we're really saying is this: let v be a composition function, and if I take the derivative of this composition function with respect to x, then I know that whenever I take the derivative of a composition function, I am taking the derivative using the chain rule. Okay. So if I do that, I know that that's going to be taking the derivative of v with respect to the outside quote unquote variable, which is y, times derivative of the inside function, which is y, with respect to the inner variable, which is x. And so that is the suggestion that we say, hey, if you have an equation that's second order and it's autonomous, and you can do this, do the substitution here, and it will basically get your equation down in order, let's say from second derivative, first derivative, then go ahead and do it. Okay. And so, of course, the note that I have here is just me going over exactly what I just said here. The main thing is to know that you need to take the derivative of v here by using the chain rule. So in noting that, step 2 just says, hey, v is a function of y, but it's going to be dy over dx. If we take the derivative of this, you see here how I've done the chain rule. And the good thing about this is that it's going to end up being the same thing every time. Okay. And so we see here that if we take the derivative of v with respect to x, is always going to be dv over dy times v. Okay. And we know that because here, this second part of the chain rule, the dy over dx, remember we just said here that dy over dx is equal to v. And so it will be this every single time. Okay. So at that point, we make the substitutions for y prime, or dy over dx, y double prime, or second derivative of y with respect to x, and it will end up looking like either v or dv over dy times v. Make those substitutions, and then after that, our resulting equations, again, either will be separable, directly integrable, first order linear, first order homogeneous, Bernoulli, or first order where we need to do linear substitution. And then, of course, depending upon what type of equation it is, we go ahead and apply those particular techniques. So this is our first example of the type where we see no y in any of the terms here. Okay. And so here is our equation. And I'm going to switch colors here so that this could look a little bit more distinct. So this first one I've already worked out for you, just to kind of show you the flow of how these problems go. Before I do that though, I do want you to notice the following here, because this is something that's going to show up later. Notice that this particular ODE, we see, in this case here, if you remember here, we're looking for something that has no y's explicitly, right? So here we see no y's in any term, but notice here we also do not see any x's in any term either. And so I'm saying that because the other technique that we talked about where, hey, we're going to let v be a function of y, but let v equal dy over dx and do the chain rule to find the derivative of it, we could also do that type of substitution and solve the same ODE. And you're going to see that later on whenever we get to that portion of the video, okay? But I just wanted you to keep that in mind, just in case you notice that. We can actually solve this particular ODE both ways, okay? All right, so using the way that we do when we have no y's, we just let v be a function of x, okay? So here v is going to be a function of x, and we let v be the derivative of y with respect to x. And so that basically means that the second derivative of y is basically going to be the first derivative of v, okay? So here we see that y prime is just v, and v prime is y double prime, okay? And so now we just do our substitutions. In place of y prime, which we have here, we have v. In place of y double prime, which is here, we have v prime, okay? Now, from here, you can see that it's relatively easy to solve this particular equation from this point. One of the things that we can do here to make this a little bit more apparent is we could write this in Leibniz form by saying dv over dx. And so now you see that, hey, I have an equation here with two different variables, v and x, and I could rearrange this equation to make it a separable one, okay? And so you see that here, if we basically divide both sides, multiply both sides by dx, we get a separable equation. And then of course from there, it's just a matter of integrating both sides of this equation, which you see here. On the left side, we're using the power rule for antiderivatives to do that. On the right side, we know that the antiderivative of 1 is always just whatever the independent variable is, which is x. And of course, both sides of these equations here have integration constants, but for simplicity, we just write it on the right side. So from this point, we know that if we multiply both sides of this equation by 2, we're going to get v squared is equal to 2x plus 2c. And here 2c is just some constant, okay? So just keep that in mind. If we take the principal root of both sides, we know that v has got to be plus or minus square root of 2x plus 2c. And so we've solved this equation now for v, but remember what we're trying to figure out is what y is. So we have to do the substitution back in. So we know here that v is the same as dy over dx. So we note that, and so now we see that this is our equation here. And now what we can do is multiply both sides by dx to get this equation here, and then just integrate both sides again, okay? Now, notice here that on the right side, I know that I can use the substitution rule, okay? And so if you're wondering, how do I know that? Well, from Cal A, one of the things that you should have learned is that whenever you're doing integration, there's sort of like this pecking order that you need to do. And the first thing that you try to do is just take the antiderivative of the integrand straight up, okay? Meaning that kind of like if you had 2x squared here, and you wanted to take the antiderivative of that. Of course, you know you just ignore the 2. You add 1 to the exponent, divide here. That's what I mean by taking the antiderivative straight up. So you can look at it and just know, hey, there's a rule I can directly apply and get the antiderivative, okay? In this case, though, you can't do what I did here. And since you can't do what I did there, the first line of defense, or the first thing that you should try, is to see, can I do U substitution, okay? And that should always be the first line of defense. If that doesn't work, then you say, hey, well, will integration by parts work? And then if that doesn't work, then you kind of go on to some of the other, integration techniques that you would use, like trig, substitution, or if you have a special type of trig integral, you'll do that. Or if you notice that you can do partial fraction expansion, you'll do that, okay? So the reason I'm saying this is that you'll see me as I go through a lot of these examples here. If I know I can't take the antiderivative straight up, the very first thing I will try to do is use substitution rule, okay? All right, so here we see that I could do the substitution rule, because if I take the derivative of what's under this square root sign here, I know that I'm just going to get a constant. And that's good enough for me, because I can rearrange that constant here, and I can find a way to represent dx in terms of w. But of course, you see we do that. And so at this point, we just go ahead and substitute everything that we need to. Take the antiderivative by using the power rule for antiderivatives. And then after that, it's just a matter of cleaning everything up to make it look nice for your answer. And we see that y of x is going to be some other integration constant, okay? And of course, notice that integration constant here, this c here, I'm going to do it like this. It should be c1 according to what I have here. So this was the first integration constant, and of course, this is the second one that comes out from doing integration again, okay? Or taking the antiderivative again. And so, I forgot I had this here. So I was actually right to keep it that way. I don't know why that's doing that. All right, so once we're here, then of course, this C1 here is just a 2C that I had, and this ends up being my final answer, okay? All right, so let's look at the next example. So for our second example, we see that we have similar situation here where we only see x, y prime, and y double prime in any of our terms here. So the thing that we don't see is we don't see any terms with y explicitly in there. So because of that, we are assuming that v is going to be a function of x. And we basically say, let v equal y prime so that v prime can equal y double prime, okay? And then from here, of course, we do the substitutions here. So y double prime is going to be v prime, and y prime here is just going to be v. And that is essentially what you see me doing here in this line, okay? So from there, then it's just a matter of rearranging the equation algebraically so that it looks like a separable equation. And then you integrate both sides. When we do the indefinite integral on the left, it's just going to be natural log absolute value of v. When we do it on the right, then of course we notice here that we could use the substitution technique or substitution rule for integration. So we let the denominator here be our substitution variable, which is w, take the derivative of w with respect to x, and we see that 2x dx can all be replaced by dw here, okay? So from that, we know that 2x dx, all that is just dw, and x squared plus 1, all that is w. We take the antiderivative of the right side, and that's going to be minus natural log absolute value of w plus the integration constant And again, this integration constant represents the one that we should have wrote on this side and this one. Okay, just move it all to one side. Now, to make life simple for ourselves here, we want to add natural log of absolute value of w to both sides here so that we get this. Now, the reason we want to do this is because here we know we have a logarithm property which says that the sum of two logarithms is going to be log of the product of what was on the inside of those earlier logarithms, okay? And of course, from there, I go and I remember that w was the same as x squared plus 1. And then I use my logarithm properties that say, really I change this logarithmic equation to an exponential one by letting what I see here be the exponents and let my base be common. And of course, the convenient one to do is e here, since I'm dealing with a natural log here. And we know that e raised to the natural log of whatever just ends up being whatever. And e raised to the c, we just copy it down here. So notice that c is a constant, and e, even though it is the base of our exponential expression, it is a constant as well. So constant raised to a constant is just going to be a constant, okay? Now, the other thing to notice here is that when we go from this step to this step, what we are using is our logarithm, not logarithm, but the absolute value properties here. Mainly here, if I know that absolute value of x is equal to a, that means here that x is either equal to plus or minus a. So that's what I'm using here to get this plus or minus on this side, okay? Now, whether this is positive or negative, it's still going to be a constant here. So for simplicity, we just let a equal plus or minus e raised to the c, because no matter what it is, it's going to be a constant. How we would be able to determine if a was going to be positive or negative, we would have to know some information about initial conditions to be able to do that. Since we don't have that in this problem, we don't worry about it, okay? All right, so moving on, at this point, and we see that we just have v times, in parentheses, x squared plus 1 equals a. Rearrange that to solve for v. That's great, but we don't want to solve for v, we want to solve for y. And we realize that v is the same as dy over dx, okay? And so therefore, this is what v was here. And then we rearrange this equation again so that we can try to solve for y. So we multiply both sides here by dx. Got this equation here. And then we just integrate both sides with respect to x. And then, of course, on the left side, that's just going to be y. On the right side, we know that this 1 over x squared plus 1, that is derivative for arctangent of x. So the antiderivative of 1 over x squared plus 1 is going to be arctangent. And we see that our final answer here just ends up being y is equal to some constant, which we call a, times arctan of x plus another constant b, where a and b are both real numbers. So for our next example here, if we look at our terms, again, we see that we only have y prime, y double prime, and x here. So we see nothing with explicitly, nothing that explicitly shows y. So we know here that we can let v be a function of x, okay? And we're also going to say where v is equal to dy over dx, or y prime, okay? Because remember, the whole goal here is to be able to do a substitution to make our order of our equation go down by 1. Since we have a second order here, we would like the highest derivative to be a first order. And so we're letting v be that function to help us to be able to make that happen. And that's what we use for our substitution. And we need to make sure that in this case, since we don't have any y showing, that v is assumed to be a function of x. So if this is the case, then of course we know that v prime, which is going to be the second derivative of y, respect to x, of course, will be y prime. And so here we will essentially just let y double prime here be v prime, and let y prime here be v. And so if we do that, then of course we got v prime plus 4v, not y. So let me change that here. Yep, so here I got a v here equals 9e raised to the minus 3x. And so if you notice, this looks like a first order linear ODE. Okay, and to be specific here, we'll switch colors. This 4 here ends up being our P, and all of this here ends up being our R. And that's important to us because we need to know that to be able to solve this first order linear ODE. Now, there are several ways that people do it. The way that I do it is I use a formula because once you kind of do all that other stuff, you end up doing this anyway. So here we're going to say that v is equal to e raised to the minus h, all that times integral of e raised to the positive h times r times dx. And after the integration is done, we go here and automatically build in our integration constant here. Okay, and all of that is going to be multiplied by e raised to the negative h, and h here is integral of p dx. Okay, and so since I already know what p is, it's just 4. If I take the integral of that, that's just going to be 4x. Normally I can do that plus some constant, but I really don't need to here because if I did it, I would recover that constant anyway in the integration. So this h is here so that we can find out our integrating factor, which is e raised to the positive h, which is just e raised to the 4x, and thus e raised to the negative h is just going to be e raised to the minus 4x. And from that, v now is just going to be equal to e raised to the negative 4x, all that integral of e raised to the positive 4x times, now we take our r here, which is 9e raised to the minus 3x times dx. So all of this is in this integration here, and then we do the plus c, have all that stuff inside the brackets there because we're going to have to multiply all of that by e raised to the negative 4x. So once that's done here, have e raised to the minus 4x. Of course, if we simplify what's going on in here, we'll have 9 integral of e raised to the x dx plus this constant, because 4x minus 3x gives us just 1x. And of course, from here, this is just e raised to the minus 4x times 9e raised to the x, because the antiderivative of e dx is just itself, plus this constant. And now we go and multiply in the e raised to the minus 4x to both terms here. And this will end up being this. And I'm just explicitly writing everything out so I make sure no one loses me. And so here's where we are. And so we see here that our v, or v of x, I should say, should be 9e raised to the minus 3x. Here, let me, plus c e raised to the minus 4x. So at this point, we found v, but the thing is that we're not trying to solve for v, right? So we need to figure out what y is. So if we go back up here, we see that we said that v was y prime, or the first derivative of y with respect to x. So here we'll say but v is equal to dy over dx, which implies that dy over dx. That doesn't look too hot, so I'm going to erase it. All right, so dy over dx, that's going to be equal to all this business here, okay? And so technically at this point, what you are looking at here is a directly integrable type of ODE, okay? Now, of course, to properly get it into that form, well, I can say if we multiply both sides by dx, at that point it would technically be separable, but with it looking like this is also directly integrable, okay? That's the point that I want to make. So we'll go ahead and go the separable route here. So if we multiply both sides by dx, this will just be dy is equal to 9 times e raised to the minus 3x plus c e raised to the minus 4x, all that times dx here. And then from there, we just integrate both sides. On the left side, we'll just write y. Remember that there will be an integration constant here, but we're going to put both of them on the right side. So you're just going to say y equals, and then here we're going to do the antiderivative of both of these terms. So for this first term here, we ignore the 9, and we know that the antiderivative of e raised to the minus 3x is going to be e raised to the minus 3x divided by a negative 3, and that is because of the substitution rule. I'm skipping it here because this is one of the ones that happens to show up a lot, so we kind of automatically know what it is. Same deal here. We have c e raised to the minus 4x, all that divided by minus 4. And then, of course, we have another integration constant. I'm just going to call it d, okay? So now at this point, I know that y is going to be 9 divided by negative 3 is 3 e raised to the minus 3x minus c over 4 e raised to the minus 4x plus d, okay? And so what I'm going to do here is I'm going to try to simplify what this looks like, and I'm just going to call this negative 3 e raised to the minus 3x plus a e raised to the minus 4x plus d, where my a here is going to be a minus c over 4. And we know that c and d are constants of integration, or just any real number. And so just for formality here, we'll just say that this is negative 3 e raised to minus 3x plus a e raised to the, let's get rid of that here, e raised to the minus 4x plus d. And so this would be our final answer here. Okay, so this will be our final example for the type of second order ODEs that we've been talking about so far. And those are type to where we only see terms that either have x and or y prime and or y double prime. What we don't see is any terms with y explicitly stated. So because of that, we let v be a function of x, and we define v to be the derivative of y with respect to x, okay? All right, so we know that we have this equation here, and notice here that we have two initial conditions here. So those integration constants that we've been seeing before, we actually have the information now to actually be able to find out what they are explicitly. So again, we see here that we do not have y in any term being shown, so that we can make this assumption here for the substitution. Because of that, then we just say that v prime, which is the same as second derivative of y with respect to x, is just going to be y double prime, okay? And so here we let y double prime be v prime, let y prime be v, and we just substitute, okay? So if we do that, then we have x times v prime plus 4 times v equals 18x squared. Now, at this point, this doesn't look like anything that we recognize, but we do see here that if I was to divide both sides of this equation by x, that I would have v prime plus 4 divided by x times v equals 18x, where of course x would not be able to equal to 0, because when I divide both sides by x here, of course I can't allow x to be 0 because that would make everything undefined at that point, okay? So what this looks like is a first order linear ODE. And of course, just like with the last example, if this is the first order linear ODE, then we know that we have our P here and our R here. That's going to go into our formula, okay? So therefore, we know that V is going to be e raised to the negative h times all this on the inside here, integral of e raised to the positive h times r times dx plus integration constant, all on the inside, okay? And here we know that h is going to be the integral of p dx. And again, this h here, this is like a middle step so that we can find out what our integrating factor is, which is actually e raised to the h. Now here, since we already know what p is, it's going to be 4 divided by x dx. This is just 4 times natural log of absolute value of x. Or we could just say this is natural log of x raised to the 4th, okay? And I purposely dropped the absolute value signs going from this step to this step, because since we have x raised to an even power, that's always going to be a non-negative quantity. No matter what value of x you plug into it, of course in this case, as long as x is greater than 0. All right, so from this point here, we know that we can just go ahead and find out our e raised to the negative h, e raised to the positive h, dump in r right here, and then just finish up solving for v here. So I'll go ahead and finish up here. So this means that v is going to be, well, actually, let me do this first. Well, I'll just do it like this, yeah. So we have e raised to the natural log of x to the 4th, e raised to the natural log of x to the 4th, and this should be a minus here. And r is going to be 18x dx plus c, and all of this is together like that. Okay, and so for here, this e raised to the negative natural log of x to the 4th, of course, this negative here could go in the exponent, and e raised to the natural log of whatever is whatever. So on the outside here, we just have e raised to the negative 4. Okay, and we're going to try to write that again to where it won't look like a y. And so inside here, with the integration, this is just going to be x raised to the 4 because of the logarithm properties there. And again, our 4s are looking like y's. All right, that's better. Times 18x to the 4 dx. And then that's plus c. And so now from here, we just have v is equal to x raised to the -4. Yeah. And all this here is just going to be 18 integral of, that looks correct here. That will be, oh yeah, this is not right because that should be 18x, not 18x to the 4. So let's get rid of that. Okay. Let's fix that. And so now this should be x raised to the 5 on the inside here. And then plus c. Okay. And then of course the antiderivative of x to the 5th is just going to be x to the 6th divided by 6 plus this constant. And 18 divided by 6 is just 3. So we have this, and this is 3x to the 6th plus c. So therefore v just ends up being 3x squared plus cx raised to the -4. Okay. Now, just like with the last example, we have solved for v here, but what we really want is y. And so we see here that v was dy over dx. So, but v is dy over dx. And thus, what that means here is that dy over dx is going to be this. Okay. Now, in the last example, what I did is I went ahead and I changed this to a separable form type of equation, and then, of course, did the integration there. This time, I'm going to recognize that this is directly integrable. Okay. So that way, I kind of look at this like how you did in first year calculus. And you can just say, all right, well, to find y, I just need to find the antiderivative of both of these terms here. Okay, and that's exactly what I'm going to do. So here the antiderivative of 3x squared is going to be 3 times x cubed divided by 3 by using the power rule. And we have c here, antiderivative of x raised to the -4 will be x raised to the -3 divided by -3. And then we will add another integration constant there, and we'll just call that d. So therefore, y, which is a function of x, is going to be x cubed, we'll say plus, I'll say a here, x raised to the -3 plus d, where a here is going to be minus c over 3 here, okay? And c and d are both real number constants. So at this point, we have our general solution for our ODE here. So what we see here is general solution. What we need is a particular solution, meaning that we need to use what we had for our initial conditions to help us to be able to find out what A and what D actually are. Okay, so we're going to use that now. So we're going to say using the first initial condition here, and that initial condition, y of 1 is equal to 8. And of course, the second initial condition, which is dy over dx, so y prime evaluated at 1 is going to be -3. Okay, and notice here that we already do have, and I'm going to write this here, y prime of x. So we don't have to go taking the derivative of this to find it. We already have it. Okay. All right, so here we're going to use this first initial value. So here, if x is 1, y is 8, then this is going to be 8 in place of this is going to be equal to 1 cubed plus a times 1 raised to negative 3 plus d. And here, this is just 1. All this will just be 1. So this will be 8 is equal to 1 plus a plus b. And here this would mean 7 is equal to a plus d. All right, so moving forward here, notice that we have dy over dx. We're going to go ahead and use that second. Let's do this again. Yeah, use this first derivative here for it. So this says dy over dx is equal to 3 times x squared plus c. And notice here that this has a. So what we want to do to kind of help ourselves a bit here is let's translate what c is in terms of a, okay, to make life a little easier for us. So here, if we see here, and we can actually leave c in here like that and just kind of do it later, but since we already see that it's going to be a problem, let's just go ahead and change it. So c here, if I was to rearrange this equation here, c is just going to be minus 3a, okay? So if I'm using y prime of 1 equals minus 3, that's the other one, initial value, then I know that for y prime of 1, the outcome is going to be minus 3. And we have 3, 1 squared. And this, instead of this c being here, this is going to be a minus 3a. So this will be a minus 3a. And then 1 raised to the negative 4. And that'll be it. And so here we'll be able to easily solve for what a is. So all this is just 3. This is just 1. So we'll just have 3 minus 3a here. So this tells us that minus 3 equals 3 minus 3a. Of course, if I subtract both sides by 3, I'll get 6. Minus 6 is equal to minus 3a. Divide both sides by negative 3, and a will end up being 2. Okay. So now that I know what a is, I know what d is. And of course here, if a is 2, then this implies that d is 5. And so now we know what our actual particular solution would be for this ODE. So be y of x is equal to x cubed plus our a is 2, x raised to negative 3, plus our d is 5. And this would be our particular solution for this ODE given our initial conditions.